Black holes. Do they erase information forever? Imagine standing at the shore of an infinite ocean where the water meets a darkness so complete that even light cannot swim back to tell you what lies beneath. This is where you find yourself now, at the edge of something extraordinary, the event horizon of a black hole. You breathe slowly, feeling the cosmic wind carry whispers of one of the universe's most beautiful mysteries. The event horizon stretches before you like a sphere of perfect silence, invisible yet profound. It is not a wall you can touch, not a barrier made of matter or energy. Instead, it is a boundary drawn by gravity itself, a line in space-time where the rules of reality begin to bend and reshape themselves into something almost unrecognizable. You cannot see this boundary with your eyes, but you can feel its presence in the way your mind reaches toward questions that have no easy answers. Light travels at 186,000 miles per second, fast enough to circle Earth more than 7 times in a single heartbeat. Throughout your entire life, light has been your faithful messenger, carrying images from the world around you to paint the pictures you see. But here, at this cosmic shore, even light surrenders. Photons that venture past the event horizon become prisoners of gravity, unable to escape back to the outside universe. They fall inward, carrying with them the last glimpses of whatever dared to cross this threshold. You close your eyes and let your imagination drift inward, following a single beam of light as it approaches the event horizon. From your perspective, watching from a safe distance, something remarkable happens. Time itself begins to slow for anything approaching the boundary. The light appears to freeze, its frequency shifting toward red as if the universe is holding its breath. Minutes pass, then hours, then years, and still the light seems suspended at the horizon, fading gradually until it becomes invisible against the darkness. But from the perspective of the light itself, if photons could have perspectives, the journey continues normally. It crosses the event horizon without fanfare, without feeling any particular moment of transition. The boundary that seems so absolute from the outside proves to be merely a coordinate on a map, meaningful only to those left behind. This is one of relativity's most gentle paradoxes. The same event can unfold in completely different ways depending on where you stand to witness it. The black hole before you formed when a massive star, perhaps 20 or 30 times heavier than our sun, reached the end of its brilliant life. For millions of years, that star had maintained a delicate balanced nuclear fusion in its core, pushing outward against gravity pulling inward. But when the fuel ran out, gravity won decisively. The star's core collapsed in less than a second, crushing atoms themselves until even the space between particles disappeared. What remains is something that challenges your everyday understanding of existence. The collapsed star has become a singularity, a point where density becomes infinite and the familiar laws of physics break down like old songs whose words have been forgotten. But the singularity itself hides behind the event horizon, veiled from the outside universe by this boundary that marks the point of no return. You find yourself wondering about information, not the kind stored on computers or written in books, but the fundamental information that defines every particle, every quantum state, every aspect of physical reality. When something falls past the event horizon, what happens to the information it carries? Does the universe forget the exact position of every atom, the precise spin of every electron, the detailed history encoded in the quantum fields? This question whispers to you like wind through autumn leaves, carrying with it centuries of human curiosity. The ancient Greeks wondered whether the universe was fundamentally knowable. Medieval scholars debated whether divine knowledge could encompass all possible information. Now, standing at the edge of a black hole, you encounter a modern version of these eternal questions. Dressed in the language of quantum mechanics and general relativity, your mind drifts to the pioneers who first imagined such objects. John Michell, a quiet English rector, calculated in 1783 that a star massive enough could trap its own light. He called these hypothetical objects dark stars. Carl Schwarzschild, working in the trenches of World War I, solved Einstein's equations to describe the space-time geometry around a spherically symmetric mass. He died of illness on the Russian front, never knowing that his solution would describe some of the most mysterious objects in the cosmos. Einstein himself resisted the idea that such extreme objects could actually exist in nature. He thought the universe too reasonable, too elegant to allow such dramatic distortions of space-time. But the universe, as you're beginning to understand, delights in exceeding even the wildest imaginations of its most brilliant observers. The event horizon surrounding the black hole has a radius that depends only on the mass of the collapsed star. For a black hole with the mass of our sun, this radius would be about 3 kilometers. For the supermassive black hole at the center of our galaxy, containing millions of solar masses, the event horizon stretches across a distance larger than Mercury's orbit. Yet in both cases the principle remains the same: cross this boundary, and you can never return to tell your story to the outside universe. You breathe deeply, tasting the strange poetry of this cosmic edge. The event horizon represents more than just a gravitational boundary. It embodies the limits of observation, the frontier between the known and unknowable. It raises questions about the nature of reality itself, about whether information can truly disappear from the universe, about whether the past can be completely erased. Standing here, you sense that this boundary holds secrets about the deepest structures of space-time and quantum mechanics. The event horizon whispers of paradoxes yet to be understood, of principles that seem to contradict each other, of a cosmic puzzle that has captivated physicists for generations. As you prepare to step deeper into this mystery, you feel a gentle anticipation building within you. The event horizon is not an ending but a beginning, the first chapter in a story about the birth of darkness itself, about how stars surrender their light to create these profound wounds in the fabric of reality. You drift backward through time, 40 million years before the event horizon whispered its secrets to you. Here, in the velvet darkness of space, a giant star burns with the fierce joy of nuclear fusion. It is 30 times more massive than our sun, a cosmic furnace whose heart reaches temperatures of hundreds of millions of degrees. You float nearby, watching this stellar giant live its accelerated life, knowing that its brilliance contains the seeds of its own inevitable surrender. The star before you is a creature of perfect balance, a delicate dance between two fundamental forces that have shaped the universe since its birth. In the core, hydrogen nuclei slam together with such violence that they fuse into helium, releasing tremendous bursts of energy that push outward against the star's own crushing weight. This is stellar equilibrium, a cosmic heartbeat that has pulsed steadily for millions of years. Each fusion reaction a tiny victory of creation over destruction. You can feel the rhythm of this stellar heart as waves of energy surge from the core toward the surface. Photons born in the nuclear fire begin an epic journey, bouncing randomly through the dense stellar material, taking thousands of years to travel from center to surface. They emerge as the light that has painted the cosmos with warmth and illumination, the same light that will one day struggle unsuccessfully to escape the event horizon you just witnessed. But as you watch, you notice subtle changes beginning to stir within the star's depths. The hydrogen fuel in the core grows scarce, like embers dimming in a cosmic fireplace. Nuclear fusion slows, and the outward pressure that has held gravity at bay for eons begins to weaken. The star responds by burning heavier elements, fusing into carbon, carbon into oxygen, oxygen into silicon. Each new fuel burns faster and hotter than the last, like a desperate attempt to maintain the equilibrium that has defined the star's existence. You witness the star's final years unfold, like a time-lapse symphony of elemental creation. In its core, a magnificent forge produces the heavy elements that will someday become planets, oceans, and life itself. Iron, nickel, cobalt, the building blocks of worlds, are born in temperatures so extreme that matter itself begins to behave in ways that challenge comprehension. Yet even as the star creates these cosmic treasures, it seals its own fate. Iron nuclei, you realize, are the most stable arrangements of protons and neutrons in the universe. When fusion tries to create elements heavier than iron, it consumes energy rather than releasing it. The stellar furnace that has burned for millions of years suddenly finds itself with fuel that won't burn. In the span of days, the core accumulates iron like ash in a dying fire, and the delicate balance that has sustained the star begins its final, irreversible shift. The collapse, when it comes, happens with breathtaking swiftness. In less than a second, a core the size of Earth shrinks to a sphere only 20 kilometers across. The matter density becomes so extreme that atoms themselves are crushed out of existence. Electrons are forced into protons, creating neutrons in a process that releases more energy in that single second than the star produced in its entire previous lifetime. You feel the shockwave of the stellar death ripple through space-time itself. The outer layers of the star, suddenly unsupported by the pressure from below, begin their own catastrophic inward journey. But they encounter the incompressible core and rebound, creating a supernova explosion that briefly outshines an entire galaxy for weeks. This stellar death will be visible from billions of light years away, a cosmic lighthouse announcing the birth of something entirely new. Yet at the very center, where the core has collapsed beyond all familiar scales, something even more extraordinary is taking shape. The density has become so extreme that space-time itself begins to curve inward upon itself, like a rubber sheet stretched beyond its breaking point. This is where darkness is truly born, not as an absence of light, but as a fundamental alteration in the geometry of reality. You watch as the collapsed core crosses a critical threshold. The escape velocity of the speed needed for anything to break free from the surface reaches the speed of light itself. Beyond this point, not even photons can escape. The event horizon forms like a one-way membrane around the collapsed matter, sealing it off from the rest of the universe. What lies within becomes forever hidden from external observation. A cosmic secret wrapped in the mathematics of curved space-time. The star that once illuminated entire solar systems has become its own opposite, a region where light goes to die, where the normal flow of information from inside to outside comes to an absolute halt. This transformation feels almost mythological in its completeness, the brightest objects in the universe giving birth to the darkest. creation and destruction intertwining in ways that speak to the deepest poetry of physical law. You sense the profound irony in this cosmic transformation. The same nuclear processes that created the heavy elements necessary for rocky planets and biological life have also created conditions so extreme that they tear holes in the fabric of space-time itself. The star's gift to the universe, the scattered wealth of heavy elements blown outward by the supernova, comes at the cost of hiding its core forever behind an event horizon. As you contemplate this stellar metamorphosis, you begin to understand that black holes are not simply cosmic vacuum cleaners or destroyers of information. They are the universe's way of storing gravitational energy in the most concentrated form possible, creating regions where the normal rules of physics are pushed to their absolute limits. The darkness born from the star's collapse is not empty darkness, it is darkness pregnant with implications for our understanding of space, time, and information itself. The collapsed core, now hidden behind its event horizon, represents matter, in a state so extreme that it challenges the very concepts of space and size. Some physicists believe it has collapsed to a mathematical point of infinite density called a singularity. Others suggest that quantum effects might prevent such infinite extremes, creating instead a state of matter so exotic that we have no words to describe it adequately. You find yourself wondering about the information that was contained in the original star, the precise position of every atom in its vast bulk, the quantum states of every particle, the detailed history encoded in its magnetic fields and rotation. Did this information disappear when the event horizon formed, or does it persist in some form that external observers can no longer access? This question pulls at your thoughts like the gentle gravity of a distant star. The birth of darkness from light represents more than just a physical transformation. It embodies a fundamental puzzle about the nature of information and reality itself. If information can be destroyed, then the universe becomes unpredictable in ways that challenge our deepest assumptions about causality and physical law. As the supernova's light begins its billion-year journey toward distant observers, and the newly formed black hole settles into its cosmic isolation, you feel drawn to explore the stage upon which this drama unfolds. The curved space-time that enables such extreme transformations deserves your attention, for it is in the geometry of reality itself that the next chapter of this mystery begins to unfold. Close your eyes and let your mind drift away from the familiar boundaries of your room, beyond the solid walls and the weight of gravity that holds you to your bed. Imagine yourself floating in the vast cosmic dark, but not as a tiny speck lost in emptiness, instead as a conscious observer witnessing the most profound truth about the universe itself. You are about to touch the very fabric from which reality is woven. Beneath you, stretching in all directions like an infinite silk sheet, lies the fabric of space-time. This is not empty void, not mere nothingness punctuated by distant stars. This is substance, as real as the air you breathe, though infinitely more subtle. Einstein saw this truth in his mind's eye over a century ago, that space and time are not separate stages upon which the cosmic drama unfolds, but rather the very material of existence itself, woven together into a single seamless tapestry. As you reach out with imaginary fingers, you can feel the texture of this cosmic fabric. It is smooth in some places, flowing like liquid mercury under your touch, but elsewhere it ripples and curves, forming gentle hills and deep valleys that stretch across dimensions your ordinary senses cannot perceive. This is the landscape of gravity itself, not a force pulling objects together, but the natural consequence of mass and energy reshaping the very geometry of existence. Watch as a star drifts past your vantage point, its enormous mass creating a depression in the space-time fabric like a bowling ball placed on a stretched rubber sheet. The curves flow outward from the star in concentric waves, growing gentler with distance but never completely disappearing. This is how the star's gravity reaches across the cosmos, through some mysterious invisible force, but by literally bending the paths that other objects must follow through space. Now, observe as a smaller object, perhaps a planet, moves through this curved landscape. It doesn't fall toward the star because some force compels it. Instead, it simply follows the straightest path available through the curved geometry, like a marble rolling along the contours of a sculpted bowl. What we experience as gravitational attraction is merely objects following the natural geodesics of bent spacetime, taking the path of least resistance through Einstein's cosmic geometry. But the true magic becomes apparent when you witness how time itself participates in this dance. Near the massive star, where spacetime curves most dramatically, time flows more slowly than in the flatter regions farther away. If you could place two identical clocks, one near the star and one in the distant, flatter spacetime, you would watch the starside clock tick more slowly, its seconds stretching like taffy in the gravitational well. This is not merely a quirk of measurement or an illusion of perception. Time itself, that most fundamental dimension of existence, runs at different rates in different regions of spacetime. The fabric you're touching is not just spatial but temporal, woven from threads of space and time so tightly interwoven that to bend one is to bend the other. As your cosmic journey continues, you encounter something that makes the fabric of space-time curve so dramatically that it forms what can only be described as a cosmic whirlpool. Here lies a black hole, and the space-time around it creates a funnel so deep and steep that even light cannot climb back out once it falls past a certain point. The event horizon. From your privileged position outside this gravitational maelstrom, you can observe the elegant mathematics of Einstein's equations made manifest. The black hole is not a tear in space-time, not a hole in the cosmic fabric, but rather the ultimate expression of the fabric's ability to curve. It is space-time bent back upon itself so severely that it creates a one-way passage, a cosmic trapdoor, through which matter and energy can enter but never return. Watch as streams of matter spiral inward toward the event horizon. Following the curved geodesics of this extreme gravitational landscape, they trace beautiful helical paths, accelerating as they fall deeper into the space-time well, heating up from friction and compression until they glow with brilliant radiation. This accretion disk becomes a lighthouse in the cosmic dark paradox, illuminating the vicinity of an object from which no light can escape. But here, at the edge of the event horizon, something extraordinary happens to information itself. According to the quantum mechanical description of reality, information cannot simply disappear, it must be preserved, even if transformed beyond recognition. Yet the classical description of black holes suggests that anything falling past the event horizon is lost forever, carrying its information into the unknowable interior. This tension between quantum mechanics and general relativity creates one of the most beautiful puzzles in modern physics, the information paradox. As you observe the cosmic scene before you, you begin to sense how information might flow like an invisible river along the curved channels of space-time. Perhaps it spreads along the event horizon itself, encoded in quantum fluctuations too subtle for ordinary observation. Perhaps it leaks slowly back into the universe through the delicate process of Hawking radiation, where virtual particle pairs at the edge of the black hole become real, with one partner escaping while the other falls inward. The implications ripple outward like waves in the space-time fabric itself. If information can flow along these curved pathways, if it can be preserved and transformed even in the most extreme gravitational environments, then perhaps the universe itself is fundamentally computational, a vast information processing system where every interaction, every curve in space-time, every quantum fluctuation contributes to an ongoing cosmic calculation. You begin to perceive that the fabric of space-time is not merely a passive stage for physical events, but an active participant in the universe's evolution. It responds to the presence of matter and energy by curving, and these curves in turn influence how matter and energy move and interact. It is a feedback loop of cosmic proportions, geometry influencing physics, and physics reshaping geometry in an eternal dance of mutual determination that your awareness expands. You sense that this cosmic fabric extends far beyond what your imagination can encompass. It curves through dimensions you cannot visualize, connecting distant regions of the universe in ways that transcend ordinary space and time. Perhaps there are wormholes, bridges through space-time that could connect black holes to distant regions of the cosmos, or even to other universes entirely. Perhaps the fabric itself is expanding, carrying galaxies apart not through their motion through space, but through the stretching of space itself. The beauty of Einstein's vision lies not just in its mathematical elegance, but in its fundamental reimagining of reality. Space and time are not fixed containers for physical events. They are dynamic, responsive, alive with possibility. They can be stretched and compressed, twisted and folded, rippled by passing gravitational waves that carry news of cosmic collisions across billions of light-years. As you float in this conceptual space, feeling the curves and flows of the cosmic fabric beneath your awareness, you begin to understand that you are not separate from this grand tapestry. Your own mass, tiny though it may be, creates its own gentle dimples in space-time. Your movement through the world traces geodesics through Einstein's curved geometry. The atoms in your body follow the same fundamental laws that govern the dance of galaxies and the collapse of stars. The fabric of space-time dreams beneath you, and in its dreams, matter and energy swirl in patterns of unimaginable complexity and beauty. Time flows like honey in some regions and races like a mountain stream in others. Information dances along quantum pathways that bridge the gap between the infinitely small and the cosmically vast. As your journey through this cosmic landscape begins to wind toward its conclusion, you carry with you a new understanding of the nature of reality itself. But even as you marvel at the elegant curves of Einstein's spacetime, deeper questions begin to surface, questions about the quantum realm that underlies this classical fabric, where uncertainty and probability reign supreme. You float just outside the event horizon, close enough to feel the immense gravitational pull, yet far enough to witness one of the most subtle and profound phenomena in the universe. Here, in the seemingly empty vacuum of space, something magical is happening. The quantum realm, which governs the behavior of the tiniest particles, is putting on a delicate light show that only the most brilliant minds have learned to see. The vacuum around you is not truly empty, despite appearances. It seethes with quantum activity, a foam of virtual particles that pop into existence for the briefest moments before annihilating. each other and disappearing back into nothingness. These particle pairs appear everywhere in the universe, but here, near the event horizon, their cosmic dance takes on special significance. You watch as pairs of particles materialize from the quantum foam like fireflies blinking in a summer twilight. Each pair consists of a particle and its antiparticle electron and positron, or photon, and antiphyted from the borrowed energy of the vacuum itself. Under normal circumstances, these pairs would quickly find each other and annihilate, returning their borrowed energy to the quantum fields and leaving no trace of their brief existence. But here, in the curved space-time near the black hole, something different unfolds. You witness the gentle tragedy of separation. As a particle pair appears near the event horizon, the immense gravitational gradient pulls one partner toward the black hole while the other drifts away into space. The particle that falls inward crosses the event horizon and vanishes from your universe, unable to return to annihilate with its partner. The remaining particle, suddenly alone and no longer virtual, becomes realer, genuine particle carrying energy away from the black hole. This is Hawking radiation, named after Stephen Hawking, who in 1974 made one of the most startling discoveries in theoretical physics. Working from his wheelchair in Cambridge, using only the tools of mathematics and imagination, Hawking revealed that black holes are not perfectly black after all. They glow with thermal radiation, like warm coals in a cosmic fireplace, slowly evaporating their mass into the surrounding space. The radiation is incredibly faint, fainter than anything you could ever hope to detect with current technology. For a black hole with the mass of our Sun, the temperature of this Hawking radiation would be about a 10 millionth of a degree above absolute zero. The black hole would be colder than the cosmic microwave background radiation that bathes the universe, making it actually absorb more energy from space than it emits. But Hawking showed that this radiation is real, a fundamental consequence of quantum mechanics operating in curved spacetime. You close your eyes and imagine yourself shrinking down to quantum scales, riding alongside the virtual particles as they dance their brief dance near the event horizon. From this perspective, you feel the strange poetry of the quantum vacuum, energy constantly borrowed and repaid, particles constantly created and destroyed, existence itself flickering in and out of reality faster than thought. The mathematics of Hawking's discovery reveals something beautiful about the relationship between gravity, quantum mechanics, and thermodynamics. The temperature of the radiation is inversely proportional to the black hole's mass. Smaller black holes burn hotter and evaporate faster, while larger ones glow more dimly and persist longer. A black hole with the mass of our Sun would take longer than the current age of the universe to evaporate completely, while a microscopic black hole would flash out of existence in a burst of energy. As you contemplate this slow cosmic evaporation, you begin to sense the profound implications of Hawking's insight. If black holes can emit radiation and lose mass, then they are not eternal prisons for matter and energy. Given enough time, vast amounts of time that dwarf the current age of the universe, even the most massive black holes will eventually evaporate completely, returning their stored mass energy to the cosmos as a gentle rain of particles and radiation. But with this beautiful discovery comes a troubling question that whispers at the edges of your consciousness. The Hawking radiation appears to be perfectly thermal, random, and featureless, containing no information about what originally fell into the black hole. It's like the difference between a detailed photograph and the warm glow of a light bulb. The photograph carries specific information about the scene it captures, while the thermal glow tells you nothing about its source except its temperature. You find yourself holding two fundamental principles of physics, watching them seem to pull in opposite directions like cosmic forces in tension. Quantum mechanics insists that information cannot be destroyed, it can be scrambled, hidden, or transformed, but the total amount of information in the universe must remain constant. This principle, called unitarity, forms one of the bedrock assumptions of quantum theory. Yet here is Hawking radiation, apparently carrying no information about the matter that originally formed the black hole or fell into it over its lifetime. If a black hole can evaporate completely through Hawking radiation, and that radiation contains no information about what was inside, then information appears to have been destroyed. The universe would have forgotten the detailed quantum states of everything that ever crossed the event horizon. This is the information paradox, one of the most elegant and profound puzzles in modern physics. It represents a conflict between two of our most successful theories: general relativity, which describes black holes as classical objects in curved spacetime, and quantum mechanics, which demands that information be preserved. Something has to give, but which principle should we abandon? You drift closer to the event horizon, feeling the strange comfort of being present at one of science's greatest mysteries. The Hawking radiation continues its gentle emission around you, each photon and particle carrying away a tiny fraction of the black hole's mass. The process is so slow that you could watch for millions of human lifetimes and notice no perceptible change. Yet the implications reverberate through the foundations of physics. Some physicists have suggested that the information might be encoded in subtle correlations within the Hawking radiation itself, patterns too complex for us to detect with current understanding, but present nonetheless. Others propose that the information never truly enters the black hole, instead being absorbed and re-emitted by the event horizon in ways that preserve quantum unity. Still others wonder whether we need to abandon our classical notions of space-time near the horizon. The paradox has inspired decades of research into the deepest questions about reality. It has led physicists to explore holographic principles, quantum entanglement, and the emergence of space-time itself from more fundamental quantum phenomena. In wrestling with this paradox, science has been forced to examine its most basic assumptions about space, time, information, and consciousness. As you float in the gentle glow of Hawking radiation, you realize that this seemingly simple phenomenon, particles separating near an event horizon, has opened a window into the deepest structures of reality. The radiation itself is beautiful in its simplicity, but the questions it raises touch on the very nature of existence and knowledge. You feel a growing sense that the resolution to this paradox might require seeing the black hole from multiple perspectives simultaneously, like viewing a crystal that reveals different facets depending on the angle of observation. Perhaps information can be both lost and preserved, depending on who is asking the question and how they choose to look for the answer. The Hawking radiation continues its patient work, slowly returning the black hole's mass to the universe one quantum at a time. But now you understand that each photon carries with it not just energy, but also one of the deepest mysteries in physics, a mystery that challenges our understanding of what it means for information to exist, to be preserved or to be lost. In the quantum dance of the cosmos, you float in the cosmic silence, cradling 2 jewels of scientific understanding in your outstretched palms. Each one glows with the accumulated wisdom of centuries, representing principles so fundamental that they seem to define the very nature of reality itself. Yet as you bring them closer together, you feel a strange tension building between them, not the comfortable harmony you might expect from complementary truths, but the electric friction of ideas that cannot easily coexist. In your left hand rests the principle of quantum unitarity, as beautiful and unforgiving as a mathematical theorem carved from starlight. This principle whispers that information is the most sacred currency of the universe, more precious than matter or energy because it can never truly be destroyed. Every quantum state, every particle interaction, every moment of cosmic history leaves an indelible mark on the fabric of reality. The universe remembers everything, encoding its entire past in the correlations between particles, in the subtle phases of quantum waves, in patterns too complex for any mind to fully grasp yet too fundamental to ignore. In your right hand glows the elegant geometry of general relativity, Einstein's masterpiece that reveals space-time as a dynamic canvas, upon which matter and energy paint their stories. This principle shows you black holes as natural consequences of extreme gravity, regions where space-time curves so severely that it closes in upon itself. Here, information appears to vanish as completely as light disappears beyond the event horizon. The thermal glow of Hawking radiation carries no memory of what created it, no signature of the complex quantum states that once fell inward past the point of no return. You feel the weight of this contradiction settle into your consciousness, like a gentle ache. These 2 principles have each proven themselves countless times in laboratories and observations, yet they seem to tell incompatible stories about what happens when matter falls into a black hole. Let your mind drift to a specific example, simple, yet profound. Imagine Alice, a quantum physicist with an adventurous spirit, decides to fall into a black hole while carrying with her a book containing the complete works of Shakespeare. Every letter, every word, every nuance of meaning in those plays represents information-specific arrangements of matter and energy that distinguish Hamlet from King Lear, that separate poetry from prose, that carry the crystallized thoughts of one of humanity's greatest minds. From Alice's perspective, falling through the event horizon feels unremarkable. She continues reading. The book remains intact in her hands, and all the information it contains travels with her toward the singularity. General relativity assures you that this information persists, at least from Alice's point of view, until the extreme tidal forces near the singularity finally overwhelm both reader and text. But from your perspective, watching from a safe distance, outside the event horizon, the story unfolds differently. You see Alice's image freeze at the boundary, growing ever more redshifted and dim as her light struggles against the gravitational field. Eventually, she fades from view entirely, and with her disappears any possibility of recovering the information. In her book, months pass, years, centuries, and the black hole continues to emit its featureless Hawking radiation, carrying no trace of Shakespeare's words back to the outside universe. The paradox deepens when you consider what happens if the black hole eventually evaporates completely through Hawking radiation. Quantum mechanics insists that the final state of Hawking particles and photons must contain, encoded somehow, all the information about everything that ever fell into the black hole. Not just Alice's book, but every star, every planet, every grain of cosmic dust that contributed to the black hole's formation. Yet the thermal nature of Hawking radiation suggests that this information has been irretrievably scrambled, transformed into random noise that tells no stories and preserves no memories. You close your eyes and let the full magnitude of this paradox wash over you like a gentle tide. It represents more than just a technical puzzle for physicists to solve. It cuts to the heart of fundamental questions about the nature of reality, knowledge, and existence itself. If information can be destroyed, then the universe becomes fundamentally unpredictable. The past would not fully determine the future, and the careful clockwork of quantum mechanics with its precise probabilities and conservation laws would break down in the presence of black holes. The implications ripple outward through physics, like waves from a stone dropped in still water. If unitarity fails near black holes, how can you trust quantum mechanics anywhere else? The theory that explains the behavior of atoms, the properties of materials, the fusion reactions in stars, and the structure of matter itself would lose its foundational principle. The universe would become a place where information could appear or disappear without cause, where the careful balance of physical law might unravel in ways too complex to predict. Yet abandoning general relativity seems equally problematic. Einstein's theory has passed every experimental test, from the precession of Mercury's orbit to the detection of gravitational waves. It describes the expansion of the universe, the bending of light around massive objects, and the precise behavior of GPS satellites. The theory that reveals black holes as inevitable consequences of stellar collapse has proven itself as reliable as any scientific principle ever discovered. You find yourself suspended between these two pillars of modern physics, feeling like a cosmic referee in a debate between titans. Each side presents compelling evidence, each has revolutionized human understanding, and each demands loyalty to principles that seem impossible to abandon. The paradox becomes a mirror reflecting the deepest questions about how science progresses, whether through revolution that overthrows old ideas, or through synthesis that finds deeper truths encompassing apparent contradictions. Some of the greatest minds in physics have wrestled with this paradox, each bringing their own perspective to the cosmic puzzle. Leonard Susskind argued that information must be preserved, even if the mechanism remains hidden from outside observers. Stephen Hawking initially believed that information could indeed be destroyed, but later changed his mind, conceding that the paradox demanded new physics beyond our current understanding. Juan Maldacena explored connections between gravity and quantum field, a theory that might resolve the conflict through holographic principles. The paradox has inspired entirely new approaches to understanding reality. It has led physicists to consider whether space-time itself might be emergent from more fundamental quantum phenomena, whether the smooth geometry of general relativity might be an approximation that breaks down near-event horizons, and whether consciousness and observation might play more fundamental roles in physics than previously imagined. As you contemplate the elegant tension between unitarity and black hole evaporation, you begin to sense that the resolution might require abandoning the assumption that there is only one correct perspective on reality. Perhaps the paradox exists because you have been trying to force a single consistent description onto phenomena that inherently transcends such simple categorization. The universe around you seems to shimmer with possibility, as if the very act of contemplating this paradox has opened doorways to deeper understanding. You sense that the answer might not involve choosing between information preservation and information destruction, but rather discovering how both can be true simultaneously, depending on how and where you choose to look for the truth. Picture yourself in an ancient cave, watching shadows dance on the stone wall before you. The flickering forms seem to tell a story, figures moving, interacting, living out their drama in silhouette. But you know these shadows are not the full reality. They are merely projections of something more complex happening behind you, in the three-dimensional world beyond the wall. Now, as you drift deeper into this cosmic meditation, prepare to discover that our entire universe might be nothing more than shadows on a wall, and that wall might be the surface of a black hole. This revelation begins with a simple question that haunted physicists for decades. What happens to information when it falls into a black hole? According to Einstein's general relativity, anything crossing the event horizon is doomed to fall toward the singularity at the center, seemingly lost forever to the outside universe. But quantum mechanics insists that information cannot simply vanish, it must be preserved, transformed perhaps, but never truly destroyed. The answer to this paradox emerged from an unexpected place: the mathematics of black hole entropy. In the 1970s, physicist Jacob Bekenstein made a startling discovery when he calculated how much information a black hole could contain. He found that its entropy, its information content, was proportional not to its volume, as you might expect, but to the area of its surface. It was as if all the information about everything that had ever fallen into the black hole was somehow encoded on the event horizon itself, like data written on a cosmic hard drive. Imagine watching a book fall into a black hole. From your perspective, outside you see the book approach the event horizon, its image growing redder and dimmer as time dilation stretches the light waves reaching your eyes. But according to the holographic principle, the book never actually disappears from your view. Instead, its information becomes encoded on the surface of the event horizon, spread out and scrambled but not destroyed. The book's three-dimensional reality has been transformed into a two-dimensional shadow. preserving all its information in a radically different form. This led to one of the most profound insights in modern physics, the holographic principle. Like a hologram on a credit card that contains a three-dimensional image encoded in a two-dimensional surface, our entire universe might be a projection from information stored on a distant boundary. The depth, the volume, the three-dimensional richness of reality as you experience it, all of this might be emerging from data encoded on a surface that exists at the edge of space itself. That as you contemplate this possibility, feel how it reshapes your understanding of existence. The chair you sit in, the air you breathe, the thoughts flowing through your mind, all of these might be holographic projections, shadows cast by information patterns on a cosmic boundary that lies beyond your perception. You are not just in the universe. You might be a pattern in the universe's holographic encoding, a thought in the cosmic mind that dreams reality into being. The mathematics supporting this vision is breathtakingly elegant. In the 1990s, physicist Juan Maldacena discovered a precise correspondence between certain types of gravitational theories in higher dimensions and quantum field theories living on their boundaries. This ADS-CFT correspondence, as it came to be known, provided the first concrete example of how a holographic universe might actually work. Complex gravitational phenomena in the bulk of space could be perfectly described by simpler quantum interactions on the boundary surface. Think of it like this. Imagine you're watching a movie projected onto a screen. The images seem to have depth and movement, telling complex stories of characters living in a three-dimensional world. But strip away the illusion, and you find that all this richness emerges from patterns of light and shadow on a flat surface. The holographic principle suggests that our cosmic movie might work the same way. All the complexity of three-dimensional space and time emerging from information patterns on a two-dimensional cosmic screen. This perspective transforms how you might think about black holes themselves. Rather than being cosmic vacuum cleaners that devour information, they become the ultimate holographic storage devices. Every particle, every photon, every bit of information that crosses the event horizon gets encoded on the surface, joining the vast library of data that chronicles everything the black hole has ever consumed. The black hole's interior might not even exist in the conventional sense. It might be a holographic projection of the information stored on its surface, but the implications reach far beyond black holes. If our universe is holographic, then the boundary on which our reality is encoded might be incredibly distant, perhaps at the cosmic horizon, the farthest edge of the observable universe. All the galaxies, stars, planets, and lifeforms that fill the cosmic expanse might be emergent phenomena, patterns arising from the holographic encoding of information on this distant boundary. This raises profound questions about the nature of consciousness itself. If your thoughts and experiences are holographic projections, what does that mean for the reality of your inner life? Are your memories encoded on the cosmic boundary? When you dream, are you accessing different patterns in the holographic data? The boundaries between physics and philosophy begin to blur when you consider that your very sense of self might be a shadow cast by information dancing on the walls of the universe. Some physicists have proposed that this holographic structure might explain the mysterious dark energy that appears to be accelerating the expansion of our universe. If space itself is emergent from holographic encoding, then the dynamics of this encoding might drive cosmic evolution. The expansion of the universe might be the result of information being processed and reorganized on the cosmic boundary, like a vast computation whose results we experience as physical reality. The holographic principle also offers new perspectives on the measurement problem in quantum mechanics. When you observe a quantum system and it collapses into a definite state, this might correspond to information being encoded more precisely on the holographic boundary. The act of measurement might be the universe updating its holographic representation, integrating new information into the cosmic database. As you lie here in the darkness, consider the profound beauty of this vision. Every sensation you feel, every thought you think, every emotion that flows through your consciousness might be shadows on the wall of Plato's cave. But these shadows are not illusions. They are the authentic expression of information patterns encoded on the boundary of reality itself. You are both the observer watching the shadows and one of the shadows being observed, a self-aware pattern in the cosmic hologram. The light that falls on your closed eyelids might be carrying information from distant stars, but according to the holographic principle, that information was already encoded on the cosmic boundary long before the photons began their journey through space. The warmth you feel might be the result of thermal patterns in the holographic encoding, temperature emerging from the information, dynamics on the two-dimensional surface that gives birth to our three-dimensional world. Even time itself might be holographic, not a fundamental dimension, but an emergent property of how information flows and changes on the boundary. The passage of moments, the flow from past to future, the arrow of time that carries you from one experience to the next, all of this might arise from the patterns of information processing on the cosmic screen. This perspective doesn't diminish the reality of your experience, it enriches it. You are not merely matter arranged in a particular pattern. You are information given form, consciousness emerging from the holographic encoding of reality itself. Your life story is written not in the atoms of your body, but in the information patterns that give those atoms meaning and purpose. That is, your mind begins to drift towards sleep. Imagine the cosmic boundary where your holographic information is stored. Picture the vast two-dimensional surface at the edge of everything, alive with patterns of information that encode not just your physical form, but your thoughts, dreams, and the infinite potential for experience that makes you uniquely you. But even as this holographic vision reveals new layers of cosmic reality, deeper mysteries remain. What lies beyond the boundary? What processes govern the encoding and decoding of information on the cosmic screen? And if our reality is holographic, what other realities might be projected from dimensions we cannot yet imagine? You float in the darkness between stars, surrounded by what appears to be empty space. But as your perception shifts to quantum scales, the void around you begins to shimmer with invisible connections, gossamer threads of correlation that stretch across cosmic distances, weaving the universe into a tapestry of interconnected existence. These are the quantum entanglements, bonds between particles that transcend ordinary notions of space and time, creating a web of relationships that Einstein once called spooky action at a distance. Imagine two particles born together in a quantum interaction, like photons emerging from the same atomic transition or electrons paired in a crystal lattice. At the moment of their creation, they become entangled, their properties become intertwined in ways that defy classical intuition. Measure the spin of one particle and find it spinning clockwise, and instantaneously, its partner will be found, spinning counterclockwise, regardless of the distance that separates them. The correlation persists across light years, as if the particles share a secret language that bypasses the speed limit of light. You close your eyes and visualize this quantum connection as a golden thread stretching between the particles, pulsing with information that flows faster than light itself. This is not information in the classical sense. No message can be sent using entanglement. No communication can occur that violates relativity. Instead, it represents a deeper kind of connection, a correlation that exists at the fundamental, a level of reality, where the universe writes its most intimate secrets. The beauty of entanglement lies in its persistence. As entangled particles drift apart, carried by cosmic winds and gravitational forces, their connection remains unbroken. One particle might fall into a black hole while its partner escapes to the far reaches of the galaxy, yet their quantum correlation continues to exist, undiminished by distance or time. The universe remembers their relationship, encoding it in the correlations between quantum states that persist across the cosmos. That this realization brings a gentle warmth to your contemplation of the information paradox. If particles that fall into black holes remain entangled with particles outside the event horizon, then perhaps the information that appears to be lost is actually preserved in these quantum correlations. The black hole might swallow the particles themselves, but the entanglement connections could serve as a cosmic memory, storing information about what fell in through the quantum relationships that survive outside the event horizon. You drift closer to the black hole, now seeing it with new eyes. The event horizon, which once seemed like an absolute barrier between the knowable and unknowable, begins to reveal itself as something more permeable to quantum information. While classical matter and energy cannot escape once they cross the boundary, quantum correlations transcend such limitations. The invisible threads of entanglement stretch across the horizon like lifelines, connecting the interior of the black hole to the outside universe in ways that preserve the essence of what was lost. Leonard Susskind and other physicists have suggested that these entanglement connections might be the key to resolving the information paradox. As matter falls into a black hole, it becomes maximally entangled with the Hawking radiation that slowly evaporates from the black hole's surface. The information that appears to be destroyed is actually encoded in the quantum correlations between the infalling matter and the outgoing radiation. To an outside observer, the information seems lost, but it persists in the entanglement patterns that connect the black hole's interior to its evaporating exterior. The picture that emerges is breathtakingly beautiful in its implications. The universe reveals itself as a quantum network where every particle maintains invisible connections to countless others. These entanglement bonds create a cosmic web of information that transcends the apparent boundaries of space and time. When you look at a single particle, you are seeing only one node in an interconnected system that spans the observable universe. Consider the Hawking radiation streaming away from the black hole, those thermal photons that carry energy but appear to carry no information about what created them. Through the lens of entanglement, these photons become something more profound. Each one carries with it quantum correlations that connect it to the matter that fell into the black hole eons ago. The information is not lost but encoded in the subtle relationships between particles, written in a language of quantum correlation that requires new mathematics to read. You feel a profound shift in your understanding of existence itself. The universe is not a collection of separate objects moving through empty space, but rather a single interconnected system where every part influences every other part through the invisible bonds of entanglement. The boundaries between objects, between yourself and the stars, between the black hole and its surrounding space become arbitrary divisions in a continuous web of quantum correlation. This interconnectedness extends beyond the present moment, reaching backward and forward through time. The particles that formed in the first moments after the Big Bang created entanglement networks that persist today, connecting the ancient cosmos to the present in ways that transcend ordinary causality. The quantum correlations that exist today carry information about the entire history of the universe, encoding the story of cosmic evolution in relationships that span space and time. The implications for the information paradox become clear as you contemplate this cosmic web. Information cannot be destroyed because it is not stored in individual particles but in the relationships between particles. When matter falls into a black hole, it takes with it one end of countless entanglement threads, but the other ends remain outside, preserving the information in quantum correlations that survive the event horizon. The black hole itself becomes part of the cosmic web, its interior connected to the exterior universe through entanglement bonds that transcend the apparent finality of the event horizon. The Hawking radiation that evaporates from the black hole carries with it the accumulated correlations of everything that ever fell in, encoding the information in patterns too subtle for classical physics to detect but fundamental to the quantum nature of reality. As you float in this web of invisible connections, you begin to understand that the question of whether information is preserved or destroyed in black holes might be asking the wrong thing entirely. Information is not a substance that can be created or destroyed. It is a property of relationships, a measure of correlation that exists in the connections between parts of the universe. The cosmic web of entanglement ensures that these relationships persist, that the universe never truly forgets anything that has ever happened within its bounds. The paradox begins to transform in your mind from a conflict between incompatible principles into a deeper recognition of the interconnected nature of existence. The universe is revealing itself as a place where nothing is ever truly lost, where every quantum event leaves permanent traces in the web of entanglement that connects all things. The black hole's event horizon, rather than being a barrier to information, becomes a membrane through which quantum correlations flow, preserving the essence of what appears to be destroyed. You sense that understanding this cosmic web might require new ways of thinking about space, time, and the nature of reality itself, ways that recognize the fundamental interconnectedness of all existence and the persistence of information in the quantum correlations that weave the universe together into a single, magnificent whole. Imagine yourself floating in the darkness of space, approaching the event horizon of a black hole. In your mind's eye, you expect to cross this boundary smoothly, following Einstein's principle of equivalence that free fall should feel no different here than anywhere else in the universe. According to general relativity, you should pass through the event horizon without noticing anything special, continuing your journey into the black hole's interior until you reach the singularity at its heart. But as you draw closer to this cosmic point of no return, something unexpected materializes before you, a wall of searing flame that exists nowhere in space and time, yet burns with the intensity of pure thought. This is the firewall paradox, one of the most beautiful and troubling puzzles in modern physics. It emerged in 2012 when physicist Ahmed Al-Hiri, Donald Marelf, Joseph Polchinski, and James Sullak, collectively known as AMPIS, discovered that our most fundamental principles of physics appear to contradict each other at the event horizon of a black hole. Like a cosmic riddle written in the language of mathematics, the firewall paradox forces us to choose between truths we hold sacred, each solution requiring us to sacrifice something we thought we understood about reality. The paradox begins with three principles that physicists have long considered unshakable. First, there is the equivalence principle, Einstein's insight that someone falling freely through space-time cannot distinguish their motion from floating in empty space. This principle suggests that crossing the event horizon should be uneventful, as smooth as stepping through an invisible doorway. Second, there is unitarity, the quantum mechanical principle that information cannot be destroyed, that the universe's total information content remains constant throughout all transformations. Third, there is the no-drama theorem, which states that nothing unusual should happen at the event horizon from the perspective of someone falling through it. For decades, these principles coexisted peacefully in the theoretical landscape, but the AMPS team discovered that when black holes begin to evaporate through Hawking radiation, when they start to give back the information they have consumed, these three principles cannot all be true simultaneously. The mathematics forces a choice, and each choice leads to a different version of reality, a different answer to the fundamental question of what it means to fall into a black hole. If you choose to preserve unitarity and the no-drama theorem, then the equivalence principle must fail, and something extraordinary must happen at the event horizon. This is where the firewall enters the story, not as literal flames, but as a region of such intense energy that any infalling observer would be instantly incinerated. The firewall would be invisible to outside observers, existing only in the reference frame of someone actually falling through the event horizon. It would be a boundary made of pure physics, a wall constructed from the contradictions inherent in our theories of space-time and quantum mechanics. But perhaps the firewall, it is not really about fire at all. Perhaps it represents something more profound. The breakdown of space-time itself at the boundary between the known and unknowable. The intense energy of this theoretical firewall might arise from the violent rupture of quantum correlations, the severing of entanglement between particles inside and outside the black hole, when information that has been quantum mechanically connected for eons suddenly finds itself forced to make an impossible choice, to be correlated with the black hole's interior or with the escaping Hawking radiation, but not both. The very fabric of space-time might respond with a kind of cosmic scream. Alternatively, you might choose to preserve the equivalence principle in unitarity, which would require abandoning the no-drama theorem. In this scenario, something dramatic and non-local must happen near the event horizon, but it need not involve a firewall. Perhaps the black hole's interior is not what it seems. Perhaps the smooth space-time of general relativity gives way to something more exotic, a region where quantum mechanics takes precedence and classical concepts of space and time lose their meaning. Or you might choose to preserve the equivalence principle and the no-drama theorem, which would require abandoning unitarity. This path leads to the most unsettling possibility of all, that information really can be destroyed, that the universe is not the perfectly reversible quantum system we thought it was. In this scenario, the act of falling into a black hole involves a genuine loss, a subtraction from the cosmic ledger of information that can never be recovered or reconstructed. Each choice opens a different doorway to understanding, but each also closes others. The firewall paradox is like a philosophical mirror, reflecting back our deepest assumptions about the nature of reality. It asks whether space-time is fundamental or emergent, whether information is truly conserved, whether the smooth continuum of Einstein's universe gives way to something more granular and quantum at the smallest scales. Some physicists have proposed that the firewall paradox reveals the limitations of thinking about black holes as isolated objects. Perhaps the solution lies in recognizing that black holes are not separate from the quantum vacuum that surrounds them, but are instead manifestations of deeper patterns in the fabric of space-time itself. In this view, the event horizon is not a boundary but a kind of interface, a place where different descriptions of reality meet and must be reconciled. Others suggest that the firewall paradox points toward a fundamental revision of our concept of time. If time itself is emergent from more basic quantum processes, then the apparent contradictions at the event horizon might dissolve when viewed from a more fundamental perspective. The firewall might be a temporal artifact, arising from our insistence on describing quantum processes using classical concepts of before and after, cause and effect. The paradox also raises profound questions about the nature of observation and measurement. The firewall exists only for someone actually falling through the event horizon. It is undetectable to outside observers, who would see nothing unusual at the boundary. This suggests that reality itself might depend on perspective, that the universe might not have a single, objective description but rather multiple, complementary ways of being understood. As you contemplate this cosmic riddle, floating in your imaginary approach to the event horizon, you begin to understand that the firewall paradox is not really about black holes at all. It is about the fundamental structure of reality, about the deep connections between information, space-time, and consciousness. The firewall becomes a symbol for the boundary between the known and unknowable, between the comfortable certainties of classical physics and the strange, probabilistic world of quantum mechanics. Perhaps the most beautiful aspect of the firewall paradox is that it refuses to be solved through compromise. Unlike many scientific puzzles that yield to incremental progress and careful experimentation, the firewall paradox demands a choice, a commitment to one vision of reality over others. It forces us to decide what we believe about the fundamental, the nature of the universe, about whether information is truly conserved, about whether space-time is smooth or granular, about whether the universe is deterministic or fundamentally probabilistic. In the end, the firewall paradox might be teaching us that reality is stranger and more wonderful than any single theoretical framework can capture. It might be showing us that the universe is not a machine to be understood through reductionist analysis, but rather a vast interconnected system where quantum mechanics, general relativity, and perhaps consciousness itself are all facets of a deeper, more unified truth. As your imaginary journey toward the event horizon continues, the firewall shimmers before you like a mirage made of pure mathematics. Whether it represents literal flame, the breakdown of space-time, or simply the limits of human understanding, it stands as a testament to the profound mysteries that still lie at the heart of physics. The firewall burns not with heat, but with the intensity of unanswered questions, illuminating the darkness at the edge of knowledge and pointing toward even deeper mysteries that await discovery in the quantum realm, where reality itself might be born from possibility. You drift through the curved space-time near the black hole, when suddenly the familiar geometry begins to reveal hidden depths. Like an ancient library with secret passages between its walls, the fabric of reality contains doorways that connect distant regions through shortcuts invisible to ordinary perception. These are the wormholes, theoretical bridges through space-time that offer the most elegant possible solution to the information paradox. while simultaneously opening new questions about the fundamental architecture of the universe. Imagine space-time as a vast sheet of paper. With our three-dimensional universe spread across its surface, a wormhole would be like a tunnel bored through the paper itself, connecting to distant points through a hidden dimension that exists perpendicular to our familiar space. What appears as an impossible journey across billions of light-years becomes a simple step through a cosmic doorway, a passage that bypasses the ordinary rules of distance and time. The mathematics of general relativity has always whispered of such possibilities. Einstein and Nathan Rosen discovered these solutions to the field equations in 1935, finding that spacetime could theoretically curve back upon itself to create bridges between distant regions. These Einstein-Rosen bridges, as they came to be known, represent some of the most exotic geometries that physics allows, yet they emerge naturally from the same equations that describe the gentle bending of light around our sun. You close your eyes and let your consciousness expand to encompass the hidden dimensions where wormholes might exist. In this realm beyond ordinary perception, the black hole before you reveals itself as more than a simple gravitational well. Its interior might connect to distant regions of space through tunnels that thread through dimensions we cannot directly observe. The event horizon, rather than being a one-way boundary to oblivion, becomes the entrance to a cosmic subway system with exits scattered throughout the universe. The implications for information preservation are profound and beautiful. When matter falls past the event horizon, it might not be trapped forever in a collapsing singularity. Instead, it could traverse the wormhole and emerge somewhere else entirely, perhaps in a distant galaxy, perhaps in a different epoch of cosmic time, perhaps even in a parallel universe with its own laws of physics. The information that appeared to be lost would actually be relocated, preserved in forms and places beyond our ability to observe. This vision transforms the information paradox from a conflict between fundamental principles into a question about cosmic geography. Information is not destroyed in black holes, it simply takes scenic routes through hidden dimensions, traveling paths that connect the interior of every black hole to the wider universe through passages we have not yet learned to map. The thermal glow of Hawking radiation might carry subtle signatures of these wormhole connections, encoding information about the hidden passages in ways too complex for current physics to decode. Juan Maldacena and Leonard Susskind have proposed that quantum entanglement itself might be the mechanism that creates these wormhole connections. In their vision, every pair of entangled particles is connected by a microscopic wormhole, a bridge through spacetime so small that it exists only at quantum scales. When particles become maximally entangled, as happens near black hole event horizons, these microscopic wormholes might merge and amplify, creating macroscopic passages that allow information to flow between the black hole's interior and the outside universe. You sense the profound poetry in this idea. The quantum entanglement that weaves the cosmic web might literally be the geometry of spacetime itself, with every entangled pair of particles connected by an invisible bridge through hidden dimensions. The universe reveals itself as a vast network of quantum tunnels, a cosmic nervous system where information flows through pathways that transcend ordinary space and time. The wormhole solution to the information paradox suggests that black holes are not cosmic prisons but cosmic transit hubs, connecting distant regions of space-time through a transportation network that operates beyond our current understanding. Every black hole becomes a doorway to elsewhere, a passage that preserves information by relocating it to places and times we cannot directly access. The apparent destruction of information becomes an illusion born from our limited perspective on the true structure of reality, yet wormholes bring their own mysteries and paradoxes. The mathematics of general relativity suggests that these passages would be inherently unstable, collapsing faster than light could traverse them unless they are held open by exotic matter with negative energy density. Such matter has never been observed in nature, leading some physicists to wonder whether wormholes represent mathematical curiosities rather than physical realities. The stability problem becomes even more intriguing when you consider the possibility of closed, time-like curves, wormhole connections that loop back through time as well as space. Such passages might allow information to travel to its own past, creating causal paradoxes that challenge our understanding of cause and effect. The universe might be filled with loops and spirals of causality that weave through dimensions beyond our perception, creating a temporal landscape as complex as any spatial geography. As you contemplate these hidden passages, you begin to sense that the question of wormhole existence might depend on subtle features of quantum gravity that current physics cannot fully address. The marriage of general relativity with quantum mechanics might reveal new forms of matter and energy that could stabilize these cosmic bridges, allowing information to flow freely between regions of spacetime that appear disconnected from a limited perspective. The holographic principle adds another layer of mystery to the wormhole picture. If the information about a black hole's interior is encoded on its surface, then wormhole connections might exist, not as physical tunnels through higher dimensions but as relationships between information encoded on different boundaries of spacetime. The passage of information through wormholes might be more like the transmission of a holographic image than the physical movement of matter through a tunnel. You float in the curved space-time near the event horizon, newly aware of the hidden passages that might thread through dimensions beyond perception. The familiar boundary between interior and exterior begins to blur as you recognize that these categories might be artifacts of limited perspective rather than fundamental features of reality. The black hole reveals itself as a node in a cosmic network of information flow, connected to the wider universe through pathways that bypass the apparent finality of the event horizon. The wormhole solution to the information paradox whispers of a universe far stranger and more interconnected than ordinary perception suggests. It hints at a reality where every black hole opens onto infinite possibilities, where information flows through channels that transcend space and time, where the apparent boundaries of existence dissolve into deeper connections that weave all things together into a single, magnificent whole. As you prepare to explore new ways of understanding these cosmic mysteries, you sense that the truth might require abandoning fixed perspectives in favor of more fluid ways of seeing, approaches that can embrace multiple viewpoints simultaneously and find harmony in apparent contradiction. Hold a crystal up to the light and turn it slowly in your hands. Watch how each face reveals itself into now showing brilliant clarity, now reflecting rainbow patterns, now appearing opaque and mysterious. The crystal is not changing its essential nature, yet it presents entirely different aspects depending on your perspective, your angle of observation, the quality of light that illuminates it. This is the gentle wisdom of complementarity, and it offers a way to resolve the deepest paradoxes of physics not through choosing sides, but through embracing the profound truth that reality itself might be multifaceted, revealing different aspects of itself to different observers. In the strange landscape of quantum mechanics, complementarity emerged as Niels Bohr's gift to our understanding of the atomic world. He recognized that light could behave as both wave and particle, not because it was confused about its identity, but because waveness and particleness were complementary aspects of a deeper reality that transcended either description alone. An electron could be both localized and spread out, depending on how you chose to observe it. Position and momentum could both be real properties, even though measuring one precisely made the other fundamentally uncertain. This quantum insight transforms how we might approach the firewall paradox and the deeper mysteries of black hole information. Rather than forcing a choice between cherished principles, between unitarity and the equivalence principle, between information preservation and smooth spacetime, complementarity suggests that these seemingly contradictory descriptions might all be true, each revealing a different facet of the black hole's multidimensional reality. Imagine yourself once again approaching the event horizon, but this time you carry with you the wisdom of complementarity. From your perspective as an outside observer, you never see anything cross the event horizon. Instead, you watch as infalling matter appears to slow down, redshift, and fade away, its information spreading across the black hole's surface like ink dissolving in water. From this viewpoint, information is perfectly preserved and coded holographically on the event horizon, accessible in principle to anyone with sufficient computational power to decode the quantum patterns written there. But now shift your perspective, become the infalling observer, riding the geodesics of curved spacetime toward the black hole's heart. From this vantage point, you pass smoothly through the event horizon, experiencing no firewall, no drama, no violation of the equivalence principle. You fall freely through what appears to be empty space, following Einstein's equations toward the singularity. In this frame of reference, information does indeed fall into the black hole's interior, seemingly cut off from the outside universe forever. Which perspective is correct? Complementarity whispers that this is the wrong question. Both descriptions are simultaneously true, like wave and particle descriptions of light. The black hole presents different faces to different observers, not because it is deceptive, but because it exists in a higher dimensional space of possibilities that cannot be fully captured by any single perspective. This dance of complementarity, it extends beyond the event horizon to encompass the very nature of spacetime itself. From one angle of observation, spacetime appears as Einstein's smooth continuum, a fabric that can be curved and warped but never torn. From another perspective, the same spacetime reveals its quantum nature, a foam of probability and uncertainty. At the smallest scales, where the very concepts of distance and duration become negotiable, the firewall paradox begins to dissolve when viewed through the lens of complementarity. The firewall exists and does not exist, depending on the reference frame and the type of observation being made. For an outside observer using quantum field theory in curved spacetime, the firewall emerges as a necessary consequence of information conservation. For an infalling observer following classical general relativity, no firewall appears, only smooth passage through seemingly empty space, but complementarity reveals something even more profound. These different descriptions are not just valid, simultaneously, they are necessarily interconnected. The wave nature of light is not separate from its particle nature. They are bound together in a deeper unity that quantum mechanics calls wave-particle duality. Similarly, the information-preserving description of black holes and the smooth space-time description might be entangled aspects of a more fundamental reality. This interconnectedness suggests that the black hole's interior and exterior are not separate regions but complementary aspects of a single quantum system. The information that appears to be destroyed from one perspective is revealed as preserved from another, not through some clever accounting trick, but through the fundamental quantum mechanical principle that reality itself is richer than any classical description can capture. Consider how this perspective transforms our understanding of measurement and observation. When you choose to measure the wave properties of light, you necessarily give up precise knowledge of its particle properties. When you choose to describe a black hole from the outside observer's perspective, you necessarily sacrifice the infalling observer's experience of smooth passage. The act of observation itself becomes a creative act, not just revealing but actually selecting which aspect of reality becomes manifest. This has profound implications for consciousness and the role of observers in physics. Perhaps consciousness itself operates through complementarity or subjective experience of flowing thoughts, complementing the objective neural processes in your brain, neither reducible to the other, both necessary for a complete description of mind. The observer and the observed might be complementary aspects of a deeper participatory universe, where consciousness and cosmos co-create each other through the act of observation. You drift deeper into this contemplation. You begin to see complementarity everywhere. Matter and energy are complementary aspects of a deeper reality that Einstein revealed through E=mc². Space and time are complementary dimensions of the unified space-time that relativity describes. Order and chaos, determinism and randomness, being and becoming all might be paired aspects of a reality too rich for any single perspective to encompass. The dance of complementarity teaches us a new way of thinking about truth itself. Rather than seeking the one correct description of reality, we learn to hold multiple perspectives simultaneously. Like a dancer who can move in several directions at once. This is not relativism, the idea that all perspectives are equally valid, but rather a recognition that reality itself might be multidimensional, requiring multiple complementary descriptions to approach completeness. In the quantum realm, this dance becomes even more intricate. Quantum superposition allows particles to exist in multiple states simultaneously until observation collapses them into a single classical state. But complementarity suggests that this collapse might not be a loss of information but rather a selection of which complementary aspect of reality becomes manifest to a particular observer. Perhaps the black hole information paradox is not a problem to be solved but a cone to be contemplated, a riddle designed to shift our consciousness from either or thinking to both. And awareness, the information is both destroyed and preserved, both inside and outside the black hole, both accessible and inaccessible, depending on the complementary perspective from which you choose to observe. As your mind settles into this gentle paradox, you find a deep peace in the recognition that reality does not need to conform to the limitations of human logic. The universe is under no obligation to make sense from any single perspective. Instead, it offers itself as an inexhaustible source of complementary truths, each one complete in itself, all of them dancing together in the great choreography of existence. The firewall burns and does not burn. Information escapes and remains trapped. Time flows and stands still. You fall forever and never fall at all. In the dance of complementarity, contradiction transforms into harmony, and the deepest mysteries of physics become invitations to expand consciousness beyond the narrow confines of classical thinking into the boundless realm where all possibilities coexist in the eternal now of quantum superposition. You stand at the edge of a vast garden where the impossible grows. Here, at the borderland between quantum mechanics and general relativity, theories bloom like exotic flowers, each one reaching toward a light that has never been seen. The air shimmers with mathematical possibility, and you breathe in the fragrance of ideas that dance between dimensions. For decades, physicists have wandered this garden, seeking the single theory that could unite the quantum realm with the cosmic stage of spacetime. They call it quantum gravity, the holy grail, that would explain how the fabric of reality behaves when matter becomes so dense, so extreme, that both quantum effects and gravitational curvature become equally important. You walk among the theoretical plantings, each one a different approach to the same fundamental mystery. String theory rises before you like a crystalline tree, its branches extending into dimensions you cannot see. In this elegant framework, the fundamental particles, electrons, quarks, photons, are revealed as different vibrations of tiny one-dimensional strings. These strings exist in a space of 11 dimensions, most of them curled up so small that they escape ordinary perception. As you run your fingers along the theoretical bark of this tree, you feel the mathematics humming beneath the surface. The beauty of string theory lies in its promise of unification. In this model, gravity emerges naturally from the vibrations of closed strings, while the other forces spring from open strings attached to multidimensional surfaces called branes. The information paradox. which seemed so insurmountable in the stark landscape of classical black holes, begins to soften here. String theory suggests that black holes might be understood as collections of strings and brains, objects that preserve information even as they appear to destroy it. You touch one of the string theory flowers, and holographic images dance in your mind. The holographic principle, born from string theory's insights, whispers that all the information contained within a volume of space can be encoded on its boundary like a three-dimensional image projected from a two-dimensional surface. If this is true, then the information falling into a black hole might never truly disappear. Instead, it could be encoded on the event horizon itself, preserved in a holographic form that appears scrambled and thermal to outside observers but retains its essential structure. Moving deeper into the garden, you encounter a different kind of beauty. Loop quantum gravity grows here like a geometric sculpture, its surface is made of discrete loops and nodes rather than smooth curves. This theory takes a more radical approach, suggesting that spacetime itself is not continuous but composed of tiny, indivisible units, atoms of space and time. At the Planck scale, smaller than any particle, reality becomes a shimmering network of quantum geometry. In loop quantum gravity, black holes take on a new character. Rather than containing true singularities where the laws of physics break down, they become quantum objects with discrete, countable internal states. The entropy of a black hole, which Hawking showed to be proportional to its surface area, emerges naturally from counting these quantum states, and crucially, information is preserved because the discrete nature of quantum geometry prevents the smooth, irreversible collapse that classical relativity predicts. You pause beside a pond where the reflected theories ripple and merge. The water shows you glimpses of other approaches: emergent gravity, where spacetime itself arises from more fundamental quantum entanglement; causal dynamical triangulation, where the universe is built from tiny geometric building blocks; and asymptotic safety, where gravity becomes scale invariant at the highest energies. Each reflection offers a different perspective on the same deep questions. As you walk, you begin to sense a pattern emerging from the diversity. Despite their different mathematical languages and conceptual frameworks, many of these theories share common insights. They suggest that information is indeed preserved in black hole evaporation, but in ways so subtle and complex that they initially escape detection. The information doesn't disappear, it transforms, becoming encoded in correlations between particles, in the structure of spacetime itself, or in holographic shadows cast on distant boundaries. The garden around you seems to pulse with a deeper rhythm. You realize that perhaps the information paradox was never really about information at all, but about the limits of classical thinking. In trying to understand black holes using the tools of traditional physics, scientists were like gardeners, trying to understand a flower by examining only its shadow. The full picture requires embracing the quantum nature of reality at its most fundamental level. Some theories suggest that black holes and their radiation exist in a state of quantum superposition, where information is simultaneously destroyed and preserved until the moment of observation collapses the possibilities into a single reality. Others propose that the interior of a black hole is connected to its exterior through quantum entanglement, creating a network of correlations that maintains information even across the event horizon. You find yourself drawn to a particularly ethereal bloomed idea that black holes might be quantum error-correcting codes, where information is distributed and protected through redundancy across multiple quantum states. This perspective transforms the black hole from a destructive force into a cosmic computer, processing and preserving information in ways that guarantee its recovery, even from apparently hopeless situations. The evening light grows softer as you continue through the garden. The theories around you seem to whisper the same essential truth, that reality is far stranger and more wonderful than classical physics suggested. The information paradox, which once seemed like a fatal contradiction, now appears as a gateway to deeper understanding. It forced physicists to question their most basic assumptions about space, time, matter, and information itself. As you reach the garden's center, you discover that the different theoretical flowers are not separate at all. Their roots intertwine beneath the surface, drawing nutrients from the same soil of mathematical possibility. String theory's holographic insights connect to loop quantum gravity's discrete geometry. Emergent gravity's entanglement webs link to causal dynamical triangulation's building blocks. They are all aspects of a single, vast understanding that human minds are only beginning to glimpse. The paradox that brought you here, the question of whether information can be destroyed, has led to something far more profound. It has revealed that the universe might be fundamentally computational, that space and time might be emergent properties of deeper quantum processes, and that the boundary between matter and information might be an illusion born of limited perspective. You feel a deep sense of peace settling over you like the garden's twilight. The information paradox has not been solved so much as dissolved, transformed from a stark contradiction into a doorway to wonder. In this place where quantum mechanics and general relativity finally learn to dance together, you glimpse the possibility that every question contains its own answer. waiting to be discovered by minds brave enough to transcend the boundaries of conventional thought. The stars begin to emerge overhead, and you sense that each point of light carries within it the seeds of infinite possibility, where the dance between information and reality continues its eternal, beautiful spiral toward understanding. In the deepening quiet of this cosmic meditation, as your journey through the labyrinth of black hole mysteries begins to circle back toward its beginning, you discover something unexpected. The question that launched this exploration, whether information can truly be destroyed when it falls into a black hole, has undergone a subtle metamorphosis. Like a river that carves new channels as it flows, the question has carved new pathways in your understanding, revealing landscapes of thought you never knew existed. You began this journey seeking a simple answer. Does information survive the plunge into a black hole's heart? Or is it erased forever from the cosmic record? But somewhere along the way, the question began to question you back. It asked what you meant by information, what you meant by survival, what you meant by forever. It whispered deeper mysteries. What is the nature of knowledge itself? How does consciousness participate in the creation of reality? What does it mean to truly understand anything at all? The black hole, that cosmic sphinx posed at the edge of space-time, has not simply withheld its secrets, it has revealed that the secrets were never separate from the seeker. The information paradox is not just about the fate of data falling into gravitational abysses. It is about the nature of mind encountering mystery, about consciousness grappling with the limits of its own comprehension. As you float in this contemplative space, you realize that the journey itself has been the answer, not the tidy resolution that textbooks provide, not the elegant solution that closes all questions, but the living process of inquiry that opens endless new vistas of wonder. The question has transformed you from a passive observer of cosmic phenomena into an active participant in the universe's ongoing conversation with itself. Consider how profoundly you have been changed by this exploration. When you first encountered the information paradox, you may have thought of information as something concrete, bits and bytes, quantum states, measurable data that could be definitively preserved or lost. But now you understand information as something far more subtle and profound. Information is the difference that makes a difference, the pattern that gives meaning to existence, the bridge between what is and what can be known. You have learned that information is not separate from consciousness. It is consciousness crystallized into form, awareness frozen into structure. When you worry about information being destroyed in a black hole, you are really asking whether the universe remembers itself, whether the cosmos is conscious in some fundamental way, whether reality has memory and meaning beyond the accident of human observation. The firewall paradox has shown you that reality itself might be multifaceted, revealing different aspects of itself to different observers. This is not a failure of physics, but a profound truth about the nature of existence, that the universe is too rich, too multidimensional, too alive to be captured by any single perspective. You have learned to hold paradox gently, not as a problem to be solved, but as a doorway to expanded awareness. Through the holographic principle, you have glimpsed that the three-dimensional world you inhabit might be a projection from a deeper two-dimensional reality. This has revealed that the boundary between inside and outside, between observer and observed, between self and cosmos, might be far more fluid than you once imagined. You are not just in the universe, you are a pattern in the universe's self-perception, a way the cosmos has of knowing itself. The dance of complementarity has taught you that contradiction is not the enemy of truth, but its most intimate partner. Wave and particle, inside and outside, preserved and destroyed, these apparent opposites are not fighting for dominance, but dancing together in the eternal choreography of existence. You have learned to think with both and rather than either or, to embrace the fundamental ambiguity that lies at the heart of quantum reality. But perhaps the most profound transformation has been in your relationship to mystery itself. You began this journey hoping to eliminate mystery, to find definitive answers that would close the question forever. Instead, you have discovered that mystery is not the absence of knowledge, but its most fertile ground. Mystery is not what remains when understanding fails. It is the inexhaustible source from which understanding continuously springs. The black hole has taught you that some questions are more valuable than their answers because they keep consciousness alive, keep it growing, keep it reaching toward greater and greater depths of comprehension. The information paradox is not a puzzle to be solved once and for all, but a living cone that continues to generate new insights, new perspectives, new ways of being in relationship with the cosmos. You realize now that the greatest physicists, Bohr, Heisenberg, Hawking, were not just problem solvers but mystery. They did not seek to eliminate wonder but to deepen it, not to close questions but to open them in ever more profound directions. Their equations were not final answers but invitations to dance with the unknown, to participate more fully in the cosmic mystery that gives birth to both questions and questioners. As your consciousness settles deeper into this recognition, you understand that you have become a different kind of being through this journey. You are no longer someone who simply wants to know whether information survives black holes, are someone who has been initiated into the deeper mystery of how knowledge and reality co-create each other, how consciousness and cosmos engage in their eternal dialogue. The black hole remains as mysterious as ever, perhaps more mysterious than when you began. But you no longer experience this mystery as frustration or failure. Instead, you feel a deep gratitude for questions that refuse to be domesticated, for riddles that continue to generate wonder, for paradoxes that expand rather than constrain your understanding of what it means to be a conscious being in an inexplicable universe. In the quantum realm, observation changes what is observed. The act of measurement participates in creating the reality it seeks to understand. Through this journey, you have become both the observer and the observed, both the question and the questioned. You have discovered that consciousness is not separate from the cosmos it contemplates, but is the cosmos contemplating itself, the universe becoming aware of its own profound mystery. The information in the black hole is both destroyed and preserved, both accessible and hidden, both lost forever and eternally present, not because physics is confused, but because reality is infinitely richer than any single description can capture. The question has no final answer because the question is alive, continuing to evolve, continuing to reveal new depths, continuing to transform everyone who encounters it with genuine openness. As sleep begins to embrace you, you carry with you, not solutions but something far more precious, a transformed capacity for wonder, a deepened appreciation for mystery, a recognition that the most profound questions are not problems to be solved but invitations to participate more fully in the ongoing creation of reality itself. The black hole spins in the darkness, keeping its secrets, but you no longer need those secrets to be revealed. You have found something more valuable than answers. You have found the eternal question that keeps consciousness alive, keeps it growing, keeps it dancing with the inexhaustible mystery of existence itself. In this recognition, you find not the end of seeking but its most beautiful beginning. As you drift into dreams where questions and answers merge into the seamless wholeness of pure wonder. Description: standing at the edge of a black hole, where light dies and meaning begins. What happens when you stare into the soul of the cosmos and it stares back in silence? This haunting journey takes you to the event horizon of a black hole, where time slows, light surrenders, and the laws of reality begin to tremble. In this emotional odyssey of space, philosophy, and physics, you'll confront the existential gravity of identity, loss, and transformation through the eyes of collapsing stars and the minds of forgotten scientists. The video explores the metaphysical poetry hidden in astrophysics and the inner black holes we carry within. From the collapse of a star's core to the silent death of photons, this narrative bridges shadow work with cosmic theory. It's a story of spiritual surrender, quantum paradox, and psychological rebirth told through the symbolism of black holes, information theory, and the myth of annihilation. In this video, you will explore the symbolic meaning of the event horizon as a spiritual threshold, emotional detachment through the lens of light's final journey, the psychological parallels between collapse and individuation, the poetry of destruction as rebirth and self-realization, how black holes mirror the mystery of human consciousness, the paradox of information loss and memory in both mind and matter, philosophical questions on permanence, identity, and cosmic silence in gravity wells, in the art of disappearing to transform. If this left a ripple in your soul, let it echo. Like, share, and subscribe. The darkness is not the end, it's the silence before rebirth. Tags: black hole, event horizon, emotional storytelling, black hole, philosophical meaning of black holes, poetic science narration, psychological storytelling, space, black hole, information paradox, space-time collapse explained, singularity, emotional metaphor, existential physics video, shadow work and cosmic symbolism, self-awareness through the universe, black hole, emotional symbolism, identity and gravitational collapse, philosophical black hole meaning, collapse of a star, emotional story, heartbreak of cosmic transformation, dark night of the soul universe, emotional rebirth through science, Carl Jung, cosmic metaphor, emotional storytelling, astrophysics, spiritual symbolism of black holes, metaphor of event horizon, gravity and emotional detachment, quantum mechanics and self-discovery, poetic narration, black hole, space and inner transformation, black hole, shadow work, surrender and identity loss, emotional depth in astrophysics, spiritual death and rebirth, inner void and cosmic meaning, image. You stand at the edge of an infinite ocean where even light forgets how to return. Darkness stretches before you like a silence that has swallowed all memory. Gravity does not pull her, it beckons with a quiet promise of erasure. Light, the eternal messenger, surrenders its last message to the void. The event horizon is not seen, it is felt like a forgotten truth beneath the skin. Time freezes at the edge, holding its breath for something unspeakable. From afar, light dies slowly. From within, it never notices the moment it vanishes. Reality bends here not with violence, but with the grace of something ancient waking. The universe whispers riddles in the silence. Between falling photons, you are not watching the collapse of a star, you are watching the collapse of certainty. Gravity wins without battle, only inevitability. The singularity hides like a secret sacred to name. You stare into the place where the rules of existence have been quietly revoked. A boundary, without edges, waits to swallow meaning itself. Even atoms surrender, crushed into the silence between thoughts. The light doesn't scream, it simply disappears. The black hole is not death, it is a question no one dares to answer. Every photon that crosses the line carries a story no one will ever read. The past collapses not in fire, but in forgotten coordinates of time. Somewhere, a star dies, and somewhere else, a mystery is born. The soul of the star becomes a wound in the fabric of space. The event horizon is a door that only opens one way into forgetting. Tap fusion turns to hunger. The furnace burns out its own heartbeat. Iron gathers like the ashes of a once living fire. Creation exhausts itself into a silence too deep for sound. The final breath of the star is not light, but collapse. A core shrinks into something smaller than memory, heavier than fate. You witness a star implode with the calm of something divine departing. The supernova screams into space, but its center says nothing. From light, we were born into light. We vanish except here. Space-time curves like a sob too deep to rise. The threshold where light fails is where truth begins. Not even escape has meaning beyond the event horizon. The star once gave birth to planets. Now it gives birth to unknowing. Where the light ends, the question begins. The universe carves a wound and stitches it with silence. You don't see the singularity. You feel its absence like a forgotten face. This is not space. It is memory with its edges burned away. The laws of physics unravel like an ancient language mispronounced. What collapses here is not matter, but meaning. Every collapse is a betrayal of equilibrium. The brightest became the darkest, without anger or regret. Darkness here is not the absence of light, is the birth of paradox. The core becomes a question, wrapped in mathematics. Even Einstein resisted until the universe insisted that the star did not die. It became something unspeakably quiet. What you witness is not violence, but the final punctuation of existence. The deeper you look, the more silence answers back. What lies within the horizon is not evil, it is eternity misunderstood. You walk away not with answers, but with awe.